Let's continue our investigation of accumulators. So we have successfully been using an accumulator to improve the definitions of the reverse and the sum functions. And that can lead us to the question whether using an accumulator would actually always be a good idea for any function that traverses a list. To consider another example here, I've written down the elem function. This is a function that we have seen in one of the first videos of this course. It checks whether a certain element is contained in a list. And it follows the standard design pattern, and we have actually been convincing ourselves by means of equational reasoning, also at the beginning of the course, how this function works and that it in principle works and does the right thing. But what about efficiency? So I'm going to start GHCi again on my file here, accumulators.hs, with this reduced stack size once more, just to get an idea. And let's do a call of elem on a list of, I don't know, let's start with 1 million elements. And we're checking for the element 0, which is not contained in this list. And we see that we relatively quickly get the answer false. And then if we make this list longer and go for 10 million elements, then we have to wait a little bit longer, but we still get to false. And at least the stack size or the stack space is not running out, apparently. And the memory use that I'm monitoring here is also okay. So what happens if I look for 100 instead? Then I get almost immediately true. And that is also something that we have been observing at the beginning of the course already. The reason for this is that 100 occurs, relatively speaking, near the beginning of the list. And whenever we consider an element here in this second equation in line 83, right, we check whether the element we're looking for, 100, is equal to the current element. And if this evaluates to true, then this call to OR here will shortcut and will immediately return true, and the recursive call does not actually have to be performed. So in a case such as this, where we check for an element that we find, we don't have to consider the long rest of the list. In fact, we could even make this list infinitely long and it would still be okay. All right. Another interesting observation is that, of course, if we are looking for 0 in the infinite list, then this function will not terminate because 0 is never found, but this will, of course, run and cost CPU, but the stack space will not run out. Right? We don't get a stack overflow, and I'm monitoring my memory use while I'm recording this video, and it stays entirely constant. And the reason for that is that if we are again in this case, and this condition evaluates to false, then the OR can still reduce, with false being the first argument. Then it reduces to just the recursive call. Right? So if we look at the general case in equational reasoning, so I'm not using concrete numbers here. Right? We are in this situation, exactly in the situation of the second case of elem. We get x equals y, or elem x ys. And now there are two situations. X equals y can evaluate either to true, right? So if x equals y evaluates to true, then we get true, or elem x ys. And then we get true. So that is, then we are completely done, right? So if x equals y, then we are in this situation. And if x is not equal to y, that, by the way, is also a way to write the not equals function. I mean, we can write not of equals, but not equals in Haskell is also available as an operator that is written as /equals. Then we get into this situation, right? So we still have the same reduction, x equals y or elemAux. Then x equals y would evaluate to false. Okay. And then the call to OR evaluates to elemAux. And this is not larger. We are not piling up something here. This is like one call of elem has been reducing to another call of elem. So we can see the expression does not get larger. The space use stays the same. So we don't have any bad behavior here. Now, you could say, okay, that's good. Now we've demonstrated that there are functions for which the normal standard design pattern without using an accumulator is not worse, but perhaps using an accumulator would still work and it would still be equally good. And then we could still use that as a default. That might be a position we can take. And as an exercise, we can certainly try to write the elem function using an accumulator. I think it's a good idea to practice more. Let me create a bit more space here so that we can see the elem function up there. So we need the equality constraint, and we need an extra accumulator argument in our elemAux function, and that is always the type of the result. So that would be a boolean here. And then we have a to list of a to bool. Okay. And then we have our accumulator, and then we have the case where we hit the empty list, and there we just spit out our accumulator. The accumulator now is a boolean that maintains whether we have already seen the element we're looking for up to this point, right? And in the situation where we're still traversing the list, we make a recursive call to elemAux, and then of course we have to update the accumulator. If we've already seen the element we're looking for up to here, then it's still fine, right? But otherwise we also have to check whether x is equal to y, and then we have to continue looking for x and y's. And then we have to write a wrapper, which I'm now going to call elem prime, so that I don't have to rename my original function. And that is, again, easy. We only have to initialize our accumulator, and the initial value of the accumulator is false, because at the beginning of the list, we have not yet seen the element we're looking for. Okay? So now let's have a look as to whether this function also works. So let's start smallish again. So let's be a little bit more careful. Let's look for 0 in a list from 1 to 10,000. And that almost immediately says false. Okay, so that's good. And oh no, this is the old function, sorry. Elem prime. And I have to reload. This still almost immediately says false. Okay, then let's make the function a bit bigger. And oh, now I'm suddenly getting a stack overflow. That's interesting. So what's going on here? Why do I suddenly get a stack overflow? This is the problem, again, that we have been observing in the sum function. We are building an accumulator here that we are not forcing. Right, look, I've not put any bangs on the accumulator in this definition. And if we make a call to elemAux with an existing accumulator, right, and we're looking, say, for 0 in the list 1 cons enum from 2 to what is it, 100,000, right? Then we are reducing this to elemAux, and let's say our accumulator is false. We're at the very beginning, right? Then our new accumulator becomes false or, right? False or, and then 0 equals 1. And then we continue with enum from to 2 and 100,000. And at this point, we are not forcing our accumulator. And in the next call, when enum from 2 reduces to 2 cons enum from 2, 3 to 100,000, we're going to add another application of the OR function to our accumulator. So we're building up a big chain of OR computations in memory in the heap. And then when we've reached the end of the list, we're going to reduce all these applications, but then they are bracketed in the wrong way. So, right, I mean, so I get something like this in the next step if I do a couple of if I do a couple of steps, right? I get something like this if I reduce a few steps further. So we get a left-nested application of OR where these things are not evaluated, and then if we have to start evaluating this, then suddenly, well, the left argument needs to be reduced, so we have to traverse this entire chain of ORs, and that costs stack space. That will make us run out of stack space. So we can try to think about, can this problem be fixed by flipping the 2 arguments around the OR? But the real problem here is, again, that the accumulator is not forced. But if we would just reduce this first application, then we would be fine. So let's just make the accumulator strict again. And again, I'm repeating, making accumulator strict is a good default. You should not even have written the first version, right? I've been doing this deliberately here to demonstrate the problem once more, but it is for accumulators, it is a really good default to always make them strict. And then if we reload and we do this, then we get false almost immediately. And then if I go to 1 million, then I also get false almost immediately. And then if I go to even 10 million, it takes me a little bit longer, but I still get false. But now if I'm asking for 100, I have to wait about the same amount of time. Whereas with the elem function, if I ask for 100, I'm almost immediately done. So we don't get our result early. And that is not surprising if we look at the definition of elem with the accumulator, or if in fact we look at any of our definitions with the accumulator. In the auxiliary function, we have 2 cases, one for the empty list and one for the non-empty list. And if you look at the one for the non-empty list, it makes a recursive call immediately. It does nothing but make a recursive call. So in particular, there is no way this function could stop at this point or even produce a part of its output. There is no way that a function could finish at the point where the list is not yet empty. And only when we reach the empty list, we're actually going to yield the accumulator. So finishing early or even partially producing results, and that becomes relevant if the results are, say, lists, is out of the question if you're using an accumulator. You always have to traverse the entire list before you return. That's the whole point of this particular structure, where you yield the accumulator on the empty list and you make a tail recursive call. You make immediately a call and do nothing afterwards or nothing around it in the cons case. So this means in particular that if we call this on an infinite list, right? It will also not work. So the original version works with looking for something that exists in the list, in an infinite list, right? But our version will just go on forever. It will now still not consume space, right? Because the accumulator is strict. The Boolean is evaluated to its topmost constructor, but for a Boolean, again, there is no further structure. The topmost constructor is true or false, so that means the Boolean is always completely evaluated. And the calls are tail calls, so there is no stack space being used, there is no heap space being used. It runs happily forever, but it will not finish, even though the accumulator is now true, right? And we would know that true is definitely the final result, but this result will not be given until we reach the end of the list. So elem is a case where I would argue the original definition is definitely better, not just because it is a little bit simpler, but also because it saves a lot of work and it never does more work than the other version. There are other functions where this is even more obvious. All right, let's consider the map function once more. Let's hide this. Let's re-implement map briefly. Map f on, well, we don't need f in the empty list case, is the empty list. Map f on x cons access is fx cons map f access. Okay. Here we are producing the list, the resulting list, and the moment we hit the cons case, we can produce the first element of the resulting list. So this is at its outermost level a call to cons. So it's not a tail call, but the outermost call is a constructor of the data type that we're interested in. And the moment we know that the result of this call to map is a cons, another function using the resulting list can already do something with the first element and can, for example, decide based on the first element or the fact that this is a cons, that it doesn't even need to look at the rest. And we see this in action in a situation where we use this together with something like take. If we say take 3 and then map +1 on an infinite list, this just works. And that is because map produces its result incrementally, right? The list is produced one element by one element, and the take function that consumes the result of the map call will only ever need the first 3 arguments or the first 3 elements of the list, and will then stop looking, and then the remaining calls to map are not needed, right? But again, this works only because we haven't written map using an accumulator, because if we had written map using an accumulator, we would be forced to traverse the entire list before we can yield any result. Furthermore, writing map using an accumulator is actually not straightforward, because the accumulator would now have to be of list type, right? But what serves us well in the reverse case, that by just putting a new element in the front of the accumulator, we automatically reverse the list, is now working against us, right? If we would want to do an efficient operation on this accumulated list that we're building up while mapping, we also would have to insert elements in the front, and then we would thereby reverse it. But if we actually want to append an element in the end of the accumulator at every step, then we get a lot of calls to appending list elements in the end again, which is entirely inefficient. So the map function is even more strongly definitely best written using this straightforward standard design pattern and not using an accumulator. So what is the general rule, or what's the rule of thumb? The rule of thumb is that if you need incremental results, such as here, structured data, you need incremental results. You want to build up your result incrementally. You want to have part of the result available while traversing the list. Then you definitely don't use an accumulator. A special case of this is where you can actually come up with the entire result before the end of the list, like in the elem case, where you can shortcut under certain in certain situations. Then you cannot and you should not use an accumulator, right? Whereas if you have to traverse the entire list anyway, such as, for example, in the reverse case, before you can produce the first element of the list, or if the operator you're using is in need of needing both its left and its right argument in order to be reduced, which is the situation in the sum case, then you're often better off with an accumulator, right? So the problem, again, for sum, if we go back to the version of sum that has been written using the standard design pattern, the problem that arises in the sum case is here, that we see in the equational reasoning here. We get this application of 1 plus and then the recursive call. And this plus operator here needs both the left and the right argument fully evaluated in order to be able to compute the plus. So we cannot reduce the plus at this point. We have to continue reducing the recursive call, and we have to therefore build the whole chain of pluses, right? In the map case, this is a cons, and cons does not need to know both its arguments. Cons immediately evaluates to itself. Cons is a constructor, right? So that's what makes that better. And or in the elem case, the or operator only needs to know its first argument in order to make actual progress, to either reduce this to a call just on the rest of the list, or to actually bail out and say we know that the result is true already. So it depends on this operator that you're using to combine the first element of the list and the recursive call. That really determines the guideline, right? Incremental results are an indicator for using the standard design pattern, not using an accumulator. An operator in use that needs to know both arguments, or having to traverse the entire list anyway before having the hope of obtaining any result, are indicators of using an accumulator, but then always make the accumulator strict by means of a bang pattern. That's the rule of thumb. I think going in more detail here is possible, and it's certainly interesting to explore this in even more nuances, but for an introduction course, I think we have to leave it at that at this time. So the next step that we're going to look at is that we've now seen quite a number of functions operating on lists, and they all fall into essentially two categories. Either they're defined directly using the standard design pattern, or they're defined using this extra step of introducing an accumulator and then essentially defining a function using the standard design pattern, but additionally using this accumulator. And we're going to look whether we cannot abstract from these and capture these patterns more precisely as higher order functions. And that's what we're going to do in the next video.